Hi everyone, in this video we are going to discuss polar bonds, but in order to do that properly we absolutely have to review the definition of electronegativity. So if you recall from previous videos, we have said that an electronegativity is essentially just an atom's ability to attract an electron. And we usually very globally can generalize this as saying that the trend for electronegativity starts off by increasing from the bottom right left-hand corner and going all the way up to the top right-hand corner. So going from the bottom left to top right, okay? So what we mean is that we have the highest electronegativity on the top right-hand corner and we have the lowest electronegativity in the bottom left-hand corner. And what we've stated before is that our most electronegative atom is fluorine, followed by oxygen, and then we have a tie between nitrogen and chlorine. But the reason we talk about this is because we want to talk about this concept of being polar. And so eventually the goal is to be able to look at a molecule and decide, is that a polar molecule or is it not? And the only way you can do that is by figuring out if the bonds inside the molecule are polar to start off with. So let's start off with a very, very simple definition of just polar. Polar is a word we're going to use if you have something that has a positive side and a negative side. So a positive and a negative side. You must be able to split the molecule in half in order for something to be a polar molecule, but we'll talk about that in a future video. So for this one, what we're trying to focus on are just the bonds specifically. So we have a polar covalent bond. Okay, this is something you need to get the definition down right now. And so a polar covalent bond is very, very simply a bond where the electrons are located next to the most electronegative atom. So it's a bond where the electrons are located next to the most electronegative atom. Okay, so remember, a covalent bond is where you're sharing electrons, but now what we're saying is that instead of sharing them perfectly equally, we're saying that it's a polar covalent bond. So the electrons are now hovering closer to the atom with the most electronegativity. So the opposite of this would be a nonpolar covalent bond. And the definition of a nonpolar covalent bond is just a bond where the electrons are shared equally. So usually we just classify this as the way we originally thought about a covalent bond. But now we're learning more about it that we want to take it a step deeper and be able to classify these bonds as either polar or nonpolar. But usually it's easiest to look at these with a visual representation. So let's look at the atom X. Okay, and so in this one we're going to say that it's the same atom, which means they have to have the same electronegativity. If you have the same atom, it has the exact same electronegativity value, okay, so it has to be the same. So if that's the case, there's no way for one atom to be more electronegative than the other, so the only way you could draw this electron cloud would be perfectly shared around these two atoms, okay, so it would look like this. That is called a nonpolar covalent bond. So that's what it would look like. Everything is equally shared. But now let's talk about when we have two different atoms. So we'll call them X and Y, and we're just going to put a bond around them. So if they're different atoms, then they have to, by definition, have different electronegativity values, okay? They have to. So for this example, we're going to say for our electronegativity that X is more electronegative than Y. So if it's more electronegative, that means the electrons are really hovering around this X instead of the Y. So we could draw our electron cloud above the XY bond, and it's definitely distorted. If you have a distorted electron cloud, then you definitely have what's called a polar covalent bond. And so now just for the example, let's draw this out one more time. Same elements, so it's X and Y. We haven't changed the elements, except for we're going to say that they still have different electronegativities, but now what I'm going to do is flip them. I'm going to reverse the electronegativity values for each one. So in this example, my X electronegativity is going to be less than my Y electronegativity. So what that means is that the electron cloud again is distorted, but this time it's hovering above the Y. So this electron cloud would look more like this. Also a polar covalent bond. Okay, so what you should be seeing here is that anytime you have different electronegativity values, you're going to have an electron cloud distortion, and if you have an electron cloud distortion, then you definitely have a polar covalent bond. So before I move any further, I want to make sure we're all on the same page, and let me ask you a question about this structure right here. For this one, where our electronegativity of X is greater than Y, which atom should be labeled our partial positive and our partial negative? Go. Did you get an answer? Hopefully you did, and all you had to do was figure out which is the more electronegative atom, which I already told you is X. So whichever one is the more electronegative atom is definitely going to be your partial negative, and then your more electropositive atom is going to have your partial positive charge, okay? So now what we're going to do is look at this one more step, take it one step deeper to see if we can actually split the bond, and hopefully that will make more sense in just a second. So all I'm going to do here is redraw these structures so it's on the screen for you to see, and in the same thing as before. So my XX have the same electronegativity. In this one, my X electronegativity is going to be greater than Y, but instead of actually mapping that out, we're going to use the partial positive and partial negatives. So for this one, our X is more negative and our Y is more positive, but for the next molecule, we're going to flip it. So my X is going to be my partial positive and my Y is going to be my partial negative. All right, so now what that means is that if I were to do this and draw out and give it a charge, I'm saying that my X is slightly more negative than my Y. And so what I can do here very, very clearly is I can draw a line between the two. I can separate my X and Y, but more importantly, I can separate my negative from my positive, okay? I can do the same thing over here. My X we said was positive, my Y we said was negative. I can clearly draw a line to separate my positive and negative side. Anytime you can do this, anytime you can separate positive and negative, you should be having this red flag go off in your mind saying polar, 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 anytime you can separate it. If you look at XX, neither one of them is more electronegative than the other atom. So I cannot put in a partial positive or a partial negative. I can't do that accurately. That's not cool. So if I try to separate my positive from my negative charge, I physically cannot do that. And so because I can't draw this line like I was able to do with my other bonds, this is a very indicative that we're looking at a non-polar bond, okay? Non-polar, you cannot separate. Polar, you can separate. I'm going to leave you with that. Take care of yourself. Drink water.